So, good afternoon, everyone. Today we have among us Dr. Sudeshna Boro Saikia, who will be delivering a talk titled Exoplanets, Atmospheres, and Habitability. And this was really a highly requested topic from our young audience members. And we are really excited to present this talk, and I hope you are excited as well. Anyway, for the information of the students, let me tell you. Dr. Sudeshna Boro Saikia obtained a master's from Glasgow University and then moved to the University of Göttingen for a PhD. Subsequently, she moved to the University of Vienna at Austria for a postdoc and is now working as an assistant professor there. So participants, please feel free to interact with the speaker. You may either type your questions in the chat box, which we shall moderate at the end, or at that, you may unmute yourself and ask the questions directly. So yeah, we can start. Over to you.
Okay, thank you. Namaskar. More আজি exoplanet বা বাহিৰ জগতৰ গ্ৰহৰ কথা ক'বলৈ পাই যথেষ্ট সুখী কিন্তু মোৰ টকটো মই ইংৰাজীত দিম কিন্তু পাছত যদি Q&A সেশনত অসমীয়াত দিব আছে কিছুমান প্ৰশ্ন অসমীয়াত উত্তৰ দিবলৈ চেষ্টা কৰিম সো আৰম্ভ কৰো তেতিয়া হলে থ্যাংক ইউ হিমাংশু ইমান ধুনীয়া ইন্ট্ৰোডাকশনটো দিয়াৰ কাৰণে সো okay let's share কৰিবলৈ পাৰিছনে
Okay. Yes. Yeah.
Okay, perfect. So hi, my name is Sudeshna, and as you know, I'm working at the University of Vienna. So I'll be talking about exoplanets, atmospheres, and habitability, more on the atmosphere side and a little bit also on the habitability of these planets. So when we talk about exoplanets, then the first things first, this is a very rapidly evolving field, and the first exoplanet was actually discovered in the 90s, in 1995, as we all know, most likely. So that was 51 Peg b, and it's actually the first exoplanet around a sun-like star. So that's something that we should remember, because there was another exoplanet which was discovered just a couple of years earlier, which was around pulsating star. So this is 51 Peg b is the kind of orbiting a star that is very similar to our own sun. So that's why it's even more exciting. Now, of course, when 51 Peg b was first discovered, it caused a little bit of controversy because it was a hot Jupiter, which means that it was a Jupiter-type gas giant, which is very hot. And the reason it's very hot is because it's orbiting very, very closely to its host star. So as a result of which, it's around 1200 Kelvin temperature, equilibrium temperature, whereas Jupiter, on the other hand, our own Jupiter has an equilibrium temperature of around 160 Kelvin. So there is a big difference between these two planets. And of course, back in those days, planet formation models told us that Jupiter-type big planets orbit quite far from the star, like our own solar system. But now we have discovered a planet that is so close, so it kind of caused a stir among planet formation theorists. But now we know this is not an exception, and there are quite a lot of planets that are as big as Jupiter. And not just that, we have discovered a wide variety of planets. And at the moment, we have more than 5,000 exoplanets that we have discovered. And what you see here is a plot from exoplanet.eu, which is a fantastic website that catalogs all the given, all known exoplanets. And I really encourage you to go to the website, have a look. You can play around with the data set, create a few different plots and histograms, etc. So what you see here essentially is the radius of a planet in terms of Earth radii versus the semi-major axis, or a distance from the host star. And if you can see my cursor here, then the first blob or the cluster of points that I'm pointing to at the top are the hot Jupiters. So these are the kind of 51 Peg b type planets. Then if you go further down, then we see that there is even a bigger cluster. And this is a cluster of planets that are particularly interesting because these are planets that lie between the size of Neptune and Earth. So they are planets that are known as sub-Neptunes, and we're going to talk about them a little bit later. But this is the most numerous kind of exoplanets that we have discovered so far. And of course, our Earth, which is this red data point, lies at 1 AU and has a radius, obviously, of 1 Earth radii. Now, if you might notice that a lot of these planets that we have discovered so far have a semi-major axis, which is much smaller than our own Earth. And that means that these planets are orbiting much closer than even Mercury's orbit around our own sun. So these are some completely different class of planets that we do not have in our own solar system. So this makes it very exciting to think about what kind of different stellar systems there might be, or there is actually. So let's go look a bit deeper into these smaller kind of planets. So of course, I call them smaller planets, but in reality, they are quite big, quite massive, because their radii is somewhere under 4 Earth radii, but between 4 Earth radii and 1 Earth radii, more or less. So what you see here is this population, and the different color here represents what kind of stars these planets are orbiting. So if you have a red, if the color is red, then it means that these are orbiting a more sun-like star. If the color is blue, then it means that these are orbiting stars that are smaller than Earth, smaller than the sun, like M stars, for example. So it tells you that it's a wide variety in the kind of stars these planets are orbiting. Now, you might be thinking that if you are concerned with habitability, if you're concerned with what kind of atmospheres habitable planets have, then why are we looking at these planets and not like planets which are similar to Earth? Now, of course, there is a problem, but before we talk about that, let's have a look into these planets themselves. So these are planets that are most numerous, so they're everywhere. These are planets that are ubiquitous in our galaxy. And of course, unfortunately, however, it's that these are the planets that we do not have in our own solar system. We have gas giants, then we have Neptune and Uranus type planets, and then we have the rocky planets like Earth, Mars, Venus, and Mercury. So where are these planets in our solar system? So these planets do not exist in our solar system, but they're everywhere else. So this makes us wonder, what kind of planets are these? So based on some preliminary planetary properties, we can provide some estimate on what to expect in terms of atmospheres for these planets. So this is why we have separated them into 2 different categories, and there are some publications associated with it, so please feel free to go look at them. So what we know now is that the top part of the plot, which are data that are planets that are more similar to in size to Neptune, they're gaseous planets. Whereas if you go further down at the bottom of this plot, towards the bottom of this plot, then we see that these are planets that are potentially terrestrial. They could have an Earth-like rocky surface, and they could have any other kind of atmosphere on top of it. So the bottom bit of this plot, or the bottom data points, are the ones that are more interesting when it comes to habitable Earth-like atmospheres. And another thing to point out, that at the where we draw the black line here, around this area, we have what is known as a transitional planet, or these are planets that could potentially be gaseous, or they could even be filled with water, and they are water worlds, as we call them. But to determine whether these planets are completely gaseous, has water, or if they are rocky with Earth-like atmosphere, we need to go and observe these atmospheres. So before we go and talk about atmospheric observations, I would like to point out that, as I said, we do not currently have many planets that are like our Earth. So this is the red area that I have just marked very broadly. And this is an area that we currently lack information on because we don't have instruments that are capable of observing and characterizing these exoplanets. But soon, in the next couple of years, we will have an European Space Agency mission known as Plato. And Plato is going to actually go and observe habitable zone planets around other stars. So this is an exciting time to do exoplanet research, and there is quite a lot more to come in the coming years. So now the question is, what is the atmospheric composition of these small, relatively small planets, sub-Neptune planets? And the reason I am more focused, or I'm going to talk a bit more about these planets at the moment, is because, as I said, we do not have habitable zone planets, but we do have a lot of relatively smaller planets about which we know nothing about. So these are the potential terrestrial planets that are accessible at the moment and in the near future, and understanding them is important because, again, they are some of the most numerous planets that we have found so far. So to do atmospheric characterization, we need to do observations. And at the moment, the European Space Agency is leading quite a lot of these initiatives. So of course, we have Webb, which is an instrument that every one of you is familiar with, I believe. And Webb is a joint NASA, ESA, and the Canadian Space Agency program. And in the last 2 years, it has already provided some incredible data, some of which we'll talk about soon. Then, of course, there is CHAOPS, which is a planet hunting mission that has been looking at some of these incredible planets that we have discovered so far. And then Plato, as I mentioned. And finally, Ariel. So Ariel is particularly interesting for exoplanet atmospheres because it's a dedicated mission that is going to do a population-wide study of exoplanet atmospheres. So it has a specific target list, and it's going to observe at least 1,000 planets and their host stars and understand what are atmospheric composition, what is the chemical composition of atmospheres of some of the most well-known planets today. So these missions that are upcoming and the next few years, you'll hear more about them, of course. So now let's talk about how do we then observe these atmospheres? How do we characterize these atmospheres? So some of you might already know much more about this, but let me just give a brief overview. So the way we observe an atmosphere, or the way we detect a planet, there are multiple different ways. But the one that is most prolific and has been used quite extensively is the transit method. So what happens is that you have a star and there is starlight coming towards us. Now, if the star has a planet that is orbiting or transiting that planet, then this is a cartoon of that star. The gray disk here and this smaller disk is the planet. And then now if you start observing this star, then let's assume that this curve here, if you see my cursor, then this is the starlight. So we are measuring the starlight, and the starlight is coming from the star uninterrupted. And as the planet now comes in front of the star, it blocks some of the starlight because the disk of the planet is blocking the light in that particular region. And that's why we see a dip in the starlight, as in there is less light now coming from the star. And now when the planet passes and goes away and transits away, then we see that the starlight is back to its original position, or its original level. And as we start, as the planet starts moving away and starts orbiting, then we do see that some of the starlight, the star here, some of the starlight does gets reflected, or does get actually light up one half of the planet, as shown in this cartoon, and this also adds an additional bit of light in the total light that's coming from the planetary system. And now, as you see, that there is more light now because this is also reflecting some of this light coming from the star. And then when this one planet goes behind the star, then some of this joint light that was coming from the system has now reduced. So we also see a smaller dip in the light as well. And then, of course, that there is this, and this, when you get the full phase curve, it's known as a phase curve when it covers one full orbit, then you get a lot of information about both the day and the night side of the planet as well. So this is how we can get information on the planets, on detection of planets, and also on the properties of the planet as well. Now, if you, more specifically, if you want to understand whether there is carbon dioxide, there is water, etc. on a planet, then what is known, what is usually used is known as transmission spectroscopy. So what happens is that, of course, the planet blocks the light because it's coming in front of the star. But if the planet has an atmosphere, and let's just say that atmosphere has water, carbon dioxide, etc., then depending on the wavelength of the light, some of these species can absorb certain wavelengths. Let's say water absorbs starlight at a wavelength around the near infrared, let's just say, and carbon dioxide absorbs the light coming from the star in mid-infrared. And then if we have an instrument that can cover that entire wavelength range, then we can see signatures of these absorption features on the spectrum coming from the star. And this is basically, you know how spectroscopy works when light passes through a prism, and it's just a little bit more complex version of that experiment that you might have done in school. So this is how now if we can do this for multiple different planetary systems, we can get a broad understanding of what kind of chemical species are present in those systems, in those planets specifically. So once we have understood that exercise, and we can do it using James Webb. So this is one of the early release data from the James Webb Space Telescope for the hot gas giant exoplanet plus 39. Now, this is basically a hot Jupiter, and this is taken in the near infrared using the near spec instrument, and that's a wavelength coverage between 0.5 up to 5 microns. And here is the wavelength in the x-axis here. And then what you see here on the y-axis is basically the amount of light that is blocked by the atmosphere. And as I said, if you have specific chemical species, then it will block and absorb light in specific wavelength. And this is what is shown by these data points in white, which is the data taken by James Webb. As you can see, these are the data points which have these very nice peaks corresponding to certain chemical species. And of course, one way of interpreting this data is to now fit an atmospheric model to the data and provide information on what is present, whether there is carbon dioxide, whether there is water, etc., and how much of it. So this is a very nice example of carrying out atmospheric characterization, and it has been very successful. We have detected CO2, water, sulfur dioxide in a lot of different other exoplanets by now as well. By different, I mean 1 or 2 that are currently available, and we expect more in the coming near future. Now, that's all and good. So we know how we can carry out this exercise and detect these complex molecules in other exoplanets. So does it mean that we are now ready to go and look at Earth-like atmospheres, or terrestrial planets, or sub-Neptunes and smaller planets? Well, don't rejoice yet. We still have a lot to do, because this is a very nice data set that was obtained by Lustig Jaeger and collaborators, and this is from their publication in 2023. So this is the spectra, or the data from JWST for a terrestrial sized planet. This is a much smaller planet compared to the previous example. And this is also JWST data. Now, what you see in the black data points are the data taken for this particular planet, and the error bars are quite high. This is again the same wavelength coverage. This is now showing a shorter part of the wavelength, and the same thing, the amount of light that is blocked by the planetary atmosphere. And unlike the previous example, we don't have these very nice peaks anymore. We more or less have a very flat kind of data set, so which doesn't show any distinctive chemical species. But nonetheless, we do see some potential shapes in the data. So now what we usually do is we take atmospheric models, and in this case, the authors took composition of solar system terrestrial planets, like a model of Earth, Venus, Mercury, and also Titan, because Titan, although it's a satellite, it still has, although it's a moon, it still has an atmosphere. And what you see here are these different now models. And as you can see, all the models fit the data quite terribly. And there is no clear distinction between the different models. One can say that they all fit the data as well or as bad. Now, this is not good, because Earth's atmosphere and Venus' atmosphere is very different. Mercury has almost no atmosphere, and Titan is also very methane heavy, has a significant amount of methane in it, which is very different from Earth's atmosphere. So now this tells us that just using this data on its own, we cannot distinguish between these different rocky planet atmospheres at the moment anyway. But again, these are just the first 2 years of data. We have a lot more data to come from JWST, and we hope to improve our understanding from these observations. And of course, we also have, in this case, we're a bit lucky in the sense that we are looking at terrestrial planets, so we can apply some knowledge that we know from our own solar system terrestrial planets and provide some constraints. But now, if we want to go for sub-Neptunes, then we have a bit of a problem there, because the data is also going to be similar because they are smaller planets. so we'll have more noise. At the same time, we don't have any solar system sub-Neptunes to learn from that we can apply to these exoplanet observations. So this is where we have to do go to theory and provide a theoretical understanding of what is actually happening in planetary atmospheres in general. So this is where we need constraints from theoretical models, and observations need this information, additional information, to provide robust characterization of these planets. So if you're doing theoretical observations, then or theoretical modeling, then we need to get an understanding of how atmospheres are formed, how they evolve, and how they survive or gets lost over time. So this is where we have to go back to stellar physics to some extent. So this is a cartoon of what's happening to a planetary system. We have the molecular cloud that's collapsing under gravitational pull, and then it leads to the formation of a protostar. And when a protostar is formed, then it also forms around it a disk, which later on leads to the formation of the planets. The planets are coming together and forming in this protoplanetary disk. Now, this happens over timescales of a few million years, and as in the next few million years, the star, which is at the center, is not just a passive object that's just sitting there. It has a magnetic field, it has winds, it has activity, it flares. So all of these together, the stellar magnetic activity, photodissociates the disk, and it evaporates the disk that is here in the Theta phase. And in the next few million years, the disk disappears. And what we are left off with is the planetary system, like our solar system, with orbiting planets. Now, I personally am interested in a planetary system once the atmosphere has formed, but of course, where that atmosphere, when and where that planet formed, and when was the atmosphere accumulated, and how it was accumulated, and what's happening in the Theta phase, for example, or even the protostar phase to some extent, is also important. So these come together to determine the fate of a planet's atmosphere. But after a planet is formed, because at this point, a sun-like planetary system would be around 10 million years old or so. So if it's 10 million years old, our sun currently is 4.5 billion years old. So over this long giga years time scale, the star is again quite active. It has magnetic field activity, and that is also impacting the atmospheres of these planets, because this I'll show in the next slide. And hence, if you want to characterize rocky planets, terrestrial planets, particularly these smaller planets, we need to consider the star and the planet together as a planetary system. And this is what we are slowly trying to do now. So what exactly is the star's role in this? So we have the central star, like our sun, and there are two main pathways that it impacts the atmosphere of a planet. Of course, I'm not talking about CME or flares here. They're also important, but these are transient events. So I'm just talking about something that all stars have. And in this case, the first is the stellar wind, which is the magnetized outflow that's coming from the star going into the interplanetary space, like our solar wind. And depending whether a planet has a magnetic field or not, this stellar wind interacts with the planet's atmosphere differently. It has an impact in atmospheric loss, but that atmospheric loss will also depend on whether the planet has a magnetic field or not. For example, in the case of Mars, where the solar wind has a big impact on the atmospheric loss, etc. Now, for most planets in our solar system, outside of our solar system, that is exoplanets, we don't know whether they have a magnetic field. We assume they have, because they should, depending on planetary interiors and how planets form. We expect that a lot of them would have magnetic field, but we do not have a direct observation yet, and we do not know what kind of magnetic field they could have, because our solar system planets, quite a few of them have magnetic fields. So that's why it is a bit difficult to constrain the exact impact on stellar wind on magnetized and unmagnetized planets. However, there is one aspect that impacts both planets, whether you have a magnetic field or not, and that is the stellar EUV. It's the high energy radiation of the star in the narrow, shorter wavelength. And what it does is that this high energy radiation, once it arrives at the upper atmosphere of a planet, it heats up the atmosphere. It leads to different photochemical reactions that leads to excessive heating, And if the UV flux or the radiation is stronger, then these processes get more have more energy, and it could lead to ionization. And when you have all of these different physiochemical processes happening, then what does happen is that if you have a complex molecule like CO2, it dissociates into carbon and oxygen. And since these are at the uppermost layer of the planet's atmosphere, then it is much easier than to get lost into space, because they easily gain enough velocity or enough speed higher than the escape velocity of the planet, and they can just get lost to space. So that's why understanding how much of these different stellar processes have an impact on a planet's atmosphere helps us to provide theoretical constraints on the atmosphere's chemistry and also survivability. And what I show here is an example from Titan, which is taken from Horst et al. And this is a cartoon based on Cassini observations of Titan. Now, this is something that we would love to have for exoplanets, but of course we cannot observe them yet in such great details. So what I show here is all of these different abbreviations on the left are different instruments from the Cassini mission, and you see a slice of the upper atmosphere of Titan. And what you see here is the thermal structure, or how the temperature changes with altitude in the atmosphere. And what you see here is at the topmost layer of the atmosphere, the EUV flux, or the high energy part of the extreme ultraviolet, leads to different photochemical reactions, which then lead to some other chemical reactions, and it can break down complex molecules into into more lightweight molecules. And if you look at the other part of the ultraviolet spectrum, then quite a bit of them also penetrate deeper into the atmosphere and drive different chemical reactions there. So as you can see, what's coming from the star has an impact on how different atmospheric chemistry is being driven. And so when we're talking about exoplanets now, we have to not just consider the physical processes, but also the chemical processes, and the star and the planet together. And just before I wrap up, a brief update on what's happening on the state of the art at the moment. And for that, I'm taking the example of the TRAPPIST-1 system. And this is a system that everyone knows, I believe. And this is a very famous multiplanetary system, which has 7 Earth-like terrestrial planets. And what you see here is actually on the x-axis, the illumination from the star, which means how much energy are these different planets receiving, normalized to Earth, which means that if it's 1, that it means that it's receiving the same amount of flux as our Earth. And the Venus, Mercury, and Mars, the solar system planets, are also shown for some reference. And as you can see, on the y-axis is the density. So B, C, D, B and C receive more flux, more energy from the star. So theoretical models do predict that these planets potentially shouldn't have any atmosphere, whereas D, E, F, G, and H could retain an atmosphere depending on the composition of the atmosphere and also the properties, and also depending on for how long that will also change for these planets. But now with JWST, we actually have observations. So this year, there were 2 papers that came out, one from Green et al. And the other one from Siba et al., where they did observations of these first 2 planets, B and C. And they have shown that these 2 planets do not have any significant or thick atmosphere. Now, of course, these by preliminary, I mean they could only observe the planet only 3 or 4 times. So we need more observations in the future. But from these observations itself, we cannot deny whether they could have a Mercury or a Mars-like atmosphere, but they definitely do not have something like a Venus-like atmosphere, for example. So this already tells us that combined with theory did predict this, and based on theoretical predictions plus actual observations, we need observations, we can actually we are slowly starting to constrain the properties of these planets and taking a step towards characterizing habitable zone planets in other stellar systems. But of course, there is a bit more work to be done to arrive there. So just to summarize, if we want to understand habitability, we should observe the atmospheres of these planets, and for them, we need observations currently with JWST and in future with missions like Ariel. But as we saw, for small planets, we also need a good theoretical understanding of what these planets are. So that's why we need to study how the star impacts atmospheric evolution, and not just the star, actually. I should also mention that there are other astrophysical processes that impact atmospheric evolution. So it's a very complex multidisciplinary problem that we should involve geologists, astrobiologists, astrochemists, solar system physicists, all have to come together if we want to finally get to a habitable zone Earth-like planet in the near future. And for that, of course, we need to know the star as well. So we have to study the star and the planet together as a combined system if we want to go for another Earth in that context. But yeah, there is a lot to be done. There is a lot of research that needs to be done, and there is a lot of more data coming. So stay tuned, and maybe some of you will be working on some of these data in the future. Yeah, thanks very much.
So thank you so much, Sudeshna, for the lovely talk. So participants, you may go ahead and type your questions in the chat box, or you may also unmute yourself and ask any questions that you might have. So even if it's not related to the talk, not any questions in astrophysics or exoplanets or whatever, we may go ahead. So anyway, by the time the participants get ready with their questions, let me go ahead and open the Q&A. Take a question from my side. So what I read a few years back, or I don't know, yeah. So scientists have also detected rogue planets, like planets that don't rotate a star, right? So what are the detection techniques that we might use to detect those planets?
Yeah, indeed. So there are a few different ways that you could potentially discover those planets. Like a colleague of mine actually here at the university, she used Gaia astrometric data. So she basically looks at the velocity fields of different stars, and also because you also have brown dwarfs, for example, and some of these planets are so big that they are as big as a star, so their gravitational force or the pull or that they would have would be very stronger than other planets as well. So astrometric data, by looking at Gaia data, they have discovered, looking at the velocities of these different objects, because they have millions of stars in the galaxy that they have observed, and they have this very complex routine that you can cluster different things and so on. So I'm not an expert on that, so I would really recommend looking into Gaia astrometric rogue planet discoveries, because that's how they do it. But another way that you could potentially discover planets, if you have something similar like a gravitational microlensing. So this is what oftentimes we have discovered some of these, because if you look at actually the data plotting the radius of the planet versus the semi-major axis, then you would see that there are one or two planets that have one Earth radii sitting at 1 AU, or maybe 2 Earth radii, not exactly 1, but 2, 3 Earth radii at 1 AU. So these are potentially habitable zone planets, but we cannot go revisit them, because these were discoveries that happened while people were looking at other stars and transients. Because if you are looking at an object and in front of it there is a star, then due to the star's gravitational field, some of the light will get bent, right? And then if you have an additional planet, then oftentimes that also includes an additional gravitational well in there. So that's what one could do it. But of course, to do these rogue planets, you would need quite big planets that are almost as big as the stars. Some of the M star, like some of the brown dwarfs, actually, not stars in this case. So you would need a few of these different methods. So and also sometimes you also do theoretical models, and from theoretical models we do know that based on what happens is that you have a gravitational n-body system which has multiple different objects in there, and then of course it's a dynamical system. Sometimes things get thrown out of orbit, and then some of these planets might get thrown out, but of course you cannot observe it. You can only predict those from theoretical models in this case. Yeah. But as I said, I'm not an expert on this, so I hope I didn't say anything wrong, but do read those papers. They are very interesting. Yeah.
Yeah, thank you so much. Actually, it does answer some of the questions. So, one more question I'd like to ask, can you briefly elaborate why the recent discovery of carbon dioxide and methane by University is such a big deal?
Yeah, sure. So first of all, some of the discoveries that, some of the plots that I did show are, for example, in Jupiter-type planets. So these are molecules that exist even in Jupiter. So depending on the temperature of the planet, depending on the pressure conditions, you would have certain molecules that you would find. Now, of course, for gas giants, it is interesting to understand what kind of chemistry is happening at the interior, what kind of temperature and pressure profile there is. And of course, we cannot observe all of these directly. We cannot say that, oh, this is what the pressure is this is the temperature at this bar pressure or whatever, right? So we want to understand the structure of the thermochemical profile of these planets by understanding what exactly, because these are trace elements. These are not, so these planets are still made up of primarily hydrogen and helium, and then we see trace elements of these other molecules. So by knowing what kind of molecules are present, we can infer what kind of properties the interior of these planets might have. So this is why for these kind of planets, it is quite exciting. And also because hot Jupiters are these very interesting hot objects. So we also want to know what's going on in there. So that because of that itself, it's quite exciting. But when you come to smaller planets, when we come to sub-Neptunes and so on, we want to discover complex species, right? Because Venus, for example, is a predominantly carbon dioxide dominated planet. We would love to see if other exoplanetary systems have a Venus-like atmosphere, because it's a rocky planet with a thick atmosphere. Based on the external and internal conditions of the planet and the surroundings, this Venus could have had a different evolutionary life if certain physical processes changed. So because of that, if we detect a CO2 atmosphere in a smaller planet, then we know that under this stellar planetary properties or conditions, certain chemical species can survive. And this tells us a lot more about what to expect later on when we go to further smaller and smaller planets. Now, of course, if we detect methane in a terrestrial planet, then the first question is, oh, why is methane there? Is it because of abiotic conditions, or is it because of because there is some is it a biosignature? But of course, methane and other chemical species do not necessarily need life to form, so they can happen due to astrophysical processes themselves. So there is a lot to be learned there. So just because we detect something doesn't mean that it tells us exactly what's going on, but it's the first step towards learning more about these exoplanetary systems. Yeah, I hope that answers the question.
Yeah, yeah. Okay, we have two questions in the chat box. If we have access to the chat box, you can check or let me know. So Priyanka, she says, ma'am, as you mentioned about the existence of atmosphere on exoplanets, so can exoplanets support life and what conditions are necessary for habitability? Okay.
Okay, that's a very loaded question. So what is habitability? Of course, depends. Our understanding of habitability stems entirely from what we know from our own Earth. So we know that at a certain surface temperature is needed, liquid water is needed for life to emerge and to develop. Now, how exactly that happened in the Earth's past is still not entirely clear, but there are certain theories about it. Now, if we want to look for exoplanets, then we can, of course, we have no idea whether methane, for example, plays a role in evolution of life. For example, even in our own solar system, Titan, for example, has a very nice atmosphere. Could it have life in the different methane pools that are on the surface? We don't know. So when we think about habitability for an exoplanet, we ignore all of these exotic processes. We only think about Earth, and we only are at the moment thinking about Earth-like conditions. So when we look at an exoplanet, we first look into what could be the temperature be on this planet, how far is it from the star, how much stellar radiation it is receiving. So we have devised these habitable zones. So depending on the stellar type, your habitable zone will be located at different distances from the star. So that's the first requirement, because this is the zone where water can be in its liquid form. So that's the first requirement. And of course, now as we are detecting more and more chemical species, we're determining different properties of other exoplanets. We are now thinking that we have to also think about survivability of certain habitable conditions, like a carbon, nitrogen, oxygen dominated atmosphere, most likely, like Earth again, over longer time scales. Because our solar system is 4.5 giga years old. That's a very long lifetime. And over that lifetime, how is the star behaving? Whether there are other impacts happening, like an asteroid impact, are then because it's a dynamical system, are there migrations happening? So all of these things come together. So we still do not have a very good answer to how do we detect a habitable planet, but we have the first very, very basic answer to this, is that we first look for the zone where we have liquid water. And from there, depending on the stellar and planetary properties, a lot more has to be looked into as well. Yeah.
Yeah. And also, I believe we humans can't be that arrogant to declare that carbon-based life form is the only life form possible. There's possibility for other life
Oh,
forms as
there
well.
could be, but there could be anything indeed. But then we go into the realms of science fiction, because we cannot quantify it. So this is where the only thing that we understand, we can only do evidence-based research on something that we know, where we have anchoring points to start from, in a way.
Exactly. We have a follow-up question, I guess. If the exoplanets exist in other solar system, and do they have their own big star like Sun in our solar system?
Yes, they they have to orbit a star in this case. I mean, of course, there are rogue planets, they don't have to orbit a star, but most exoplanets are detected around other stars, and some of them do orbit stars like our sun. Our sun is actually not a big star. It's a relatively average kind of a star. There are even bigger, hotter stars than our sun. We have detected a few around those stars, but most of the planets that we have discovered or are going to study actually in the immediate future, or are studying at the moment, are planets around smaller stars. These are stars that are much smaller than our sun and redder in color as well. So these are the stars that are mostly looked into when it comes to exoplanets.
Okay, let's say you're studying a planet that is orbiting a binary, not a single star, but a binary. So, do the light curve modeling and all those things get very difficult in that case?
It does actually, yeah. Depends also how the planet is orbiting the star, and which one it is transit. So that depends on a few different things. First of all, is it orbiting both of the stars, or is it orbiting a single one of the binary star? Because it could have its orbit in different architecture. And then the question is it transiting one of those stars? It has to transit to be able to do this light curve modeling. But if you're doing radial velocity measurements, in principle, you can detect them easily, but it's still, you have to know the binary system quite well for that. So yeah. But there has been discoveries around these for sure, yeah.
Okay, we have another question from Liponjati. You can see that correctly. Well, we have mentioned about Titan that had an atmosphere of methane. If Titan is the natural satellite of Saturn, doesn't the Saturn have the same atmosphere as Titan? Okay. If yes, why do we take the example of Titan but not Saturn? Okay.
So Saturn is a gas giant, so its primary constituent is hydrogen and helium. And of course, it has trace elements of methane and other species as well. It's not that it doesn't. But why Titan is interesting is because Titan has methane, but methane is not the dominant constituent. It's actually a nitrogen-dominated atmosphere, like our Earth. But methane is a strong constituent, unlike Earth, for example. And because Titan has an atmosphere which is thick enough, and that's why it's interesting, and because it has liquid or liquid on its surface, which is liquid in the sense that these are methane reservoirs that are on the surface. So now the question is, if you want to think about habitability, then Titan is a very good source because it has loads of complex hydrocarbons, and it has a lot of complex organic chemistry that's going on in Titan. That's why it's interesting from an organic chemistry point of view, from an astrobiology point of view. Now, of course, we still don't know much about Titan because we have only have observations from these big missions that went into Saturn, then also from information from other missions that were sent out to look at other objects in that part of the solar system. But we have a lot of upcoming missions that are going to look into Titan. So yeah.
Yeah. Okay. So, one more question. This time from Neil Pawan. Do exoplanets exist only around the star? Can life forms exist on a planet orbiting a black hole or something? Or some other stars?
Yeah, of course. I mean, a black hole at some point in its life was a star, quite a few of the black holes, right? So this is the end state of a star's lifetime in a way. So of course, what happens is that they could also have exoplanets in the past. The problem is that once you arrive at that late evolutionary stage of a star's lifetime, most stars, like our sun, for example, will start expanding, and then they will engulf the planets. It will be basically a catastrophic event from stellar evolution perspective. So planets will not remain as they are at the moment. So for example, there has been some observations around white dwarfs where they have seen a lot of debris around it, which are, one theory is that these are leftovers from the time when the planets were destroyed because of the stellar evolutionary stage, because the star, a main sequence star, will start evolving and eventually get into these different exotic objects. Now, of course, there has been a few, I think 1 or 2 recent discoveries where they might have detected an intact planet around the white dwarf. I don't know whether this is absolutely confirmed or it's a potential candidate. So it might have been a confirmed planet, but I'm not quite sure about that yet. So yeah, they can exist if they survive these catastrophic events that leads to the formation of a black hole from a star. Yeah, of course they could, but it is quite unlikely. But again, the first exoplanet ever discovered was around a pulsating star. So that already is a very exotic element in a stellar during the late stage of a star's lifetime. So it's not unlikely, but I'm not sure if there is any discovery of, I don't think there has been any discovery of an exoplanet around a black hole. So yeah.
Okay, so no more questions in the chat box as of now. Any participant, if you want to speak directly or ask any question directly, you can go ahead and unmute yourself. And the questions need not be in English. You can also use SMS.
Yes.
অসমীয়াটো সুধিব পাৰা, একো problem নহয়. Maybe any other question related to applying abroad, let's say in European universities. তেনেকুৱা ধৰণৰ questions আহিলেও বেয়া নহয়. So anyone? Okay, maybe not. Anyway, মই তেন্তে সুধি দিওঁ বস্তুটো যে ইউৰোপিয়ান ইউনিভাৰ্চিটিজত এপ্লাই কৰাৰ বা তেনেকুৱা কিবা টিপছ এণ্ড ট্ৰিক্স বা তেনেকুৱা চামথিং কিবা তাৰ ওপৰত অলপ ক'ব নেকি? ভেৰি ব্ৰিফলি।
Generally, ইয়াত মাষ্টাৰ্ছ বা বেচেলাৰ্ছ লেভেল কৰিবলৈ হ'লে এপ্লাই কৰিব লাগে। ইয়াত জেনেৰেলি সেনেকুৱা একো স্কলাৰশ্বিপ চিষ্টেম সেনেকুৱা নাই, কিন্তু কাণ্ট্ৰি ৱাইড থাকিব পাৰে, ধৰা যেনেকে জাৰ্মান আৰু ইণ্ডিয়ান গভৰ্ণমেণ্ট কিছুমান প্ৰগ্ৰামছ থাকিব পাৰে যিহেতু তাৰ পৰা স্কলাৰশ্বিপ পোৱাৰ সুবিধাটো থাকে। কিন্তু মই জনা মতে সেনেকে সিমান স্কলাৰশ্বিপৰ সুবিধা নাই মাষ্টাৰ্ছ বেচেলাৰ্ছ লেভেলত। কিন্তু PhD কৰিবলৈ হলে PhD কাৰণে এপ্লাই কৰিবলৈ জৰুৰী এপ্লাই কৰিব লাগিব আৰু আজিকালি PhD প্ৰগ্ৰাম বিলাকত এপ্লাই কৰিবলৈ হলে যথেষ্ট কম্পিটিটিভ মানে কি এতিয়া ধৰা মই যেতিয়া PhD কাৰণে এপ্লাই কৰিছিলো বেছি এপ্লিকেশ্যন নহৈছিলে ইমান বেছি এটা PhD পজিশ্যনৰ কাৰণে আজিকালি এই বছৰ মই এটা PhD প্ৰগ্ৰামত আমাৰ এপ্লিকেশ্যন কিছুমান চাবলগীয়া হৈছিলে তাত তোমাৰ 60-70টা এপ্লিকেশ্যন আহিছে এটা পজিশ্যনৰ কাৰণে গোটেই পৃথিৱীৰ পৰা অসমৰ পৰা বুলিয়ে নহয় অসমৰ পৰাও আহিছে অন্য জেগাৰ পৰাও আহিছে বা ৰাছিয়াৰ পৰা আহিছে বা সব জেগাৰ পৰা আহিছে ধৰা কিন্তু সেনেকুৱা 60-70টা এপ্লিকেশ্যন আহিলে জেনেৰেলি কি হয় এপ্লিকেশ্যন বিলাক প্ৰথমতে তোমাৰ সায়েন্টিষ্ট বা ৰিচাৰ্চাৰ বা প্ৰফেচৰ বা যিবিলাক মানুহে ধৰা এমপ্লয় কৰিব যিবিলাক মানুহে গাইড কৰিব ছুপাৰভাইজ কৰিব তেওঁলোকে প্ৰথমতে এপ্লিকেশ্যনখিনি নাপায় প্ৰথমতে এপ্লিকেশ্যন যায় এডমিনিষ্ট্ৰেটৰৰ তাত গৈ পেলাই চিলেকশ্যন হয় তাৰপাছত নেক্সট চিলেকশ্যন হয় সেনেকে জেনেৰেলি মানে বহুত কেইবাটাও ষ্টেপত চিলেকশ্যন হয় আৰু সেই চিলেকশ্যন বিলাকত বহুত কম্পিটিটিভ এইকাৰণে হয় কাৰণ CV চাই ষ্টেটমেণ্ট চাই বহুত কিবা কিবি ডকুমেণ্ট চাই আৰু সেই তেতিয়াতে কি হয় যে বহুত ল'ৰা ছোৱালীৰ এপ্লিকেশ্যন বিলাক বাহিৰ কৰিবলগীয়া হয় কাৰণ বহুত হাইলি স্পেচিফিক আৰু হাইলি তোমাৰ কোৱালিফাইড ল'ৰা ছোৱালী কিছুমানে এপ্লাই কৰে তেতিয়া মানে কি হয় কাৰোবাৰ যদি অলৰেডি PhD কৰাৰ আগতে দুখন ৰিচাৰ্চ জাৰ্নেল আৰ্টিকেলত পাব্লিকেশ্যন আছে তেতিয়া সেই মানে এপ্লিকেণ্টজনৰ গৰাকীৰ চান্সটো বাঢ়ি যায় নহয় জানো সেনেকা হলে মানে কি কম্পিটিটিভ নহয় মই এটা কথা লক্ষ্য কৰিছো যে আমাৰ ভাৰতৰ পৰা অহা ল'ৰা ছোৱালী বা অলপ ইউৰোপৰ যিবিলাক নহয় বা ইউৰোপ আমেৰিকাৰ নহয় অন্য জেগাৰ পৰা অহা ল'ৰা ছোৱালী সেনেকুৱা অকণ কম্পিটিটিভ লেভেলটো আচলতে কম্পিট কৰিবলৈ অলপ দিগদাৰ হয় আজিকালি কাৰণ আজিকালি ইউৰোপ আমেৰিকা এনেকুৱা জেগাত মাষ্টাৰ্ছ লেভেলতে বহুতে ডাঙৰ প্ৰজেক্ট কৰে ডাঙৰ পাব্লিকেশ্যন উলিয়ায় তেতিয়া আচলতে এইটো আনফেয়াৰ হৈ যায় যে কি আমাৰ ল'ৰা ছোৱালীবিলাকে নোৱাৰে তেতিয়া কম্পিট কৰিবলৈ তো মোৰ সেইটো কাৰণে এটা কথা ক'বলৈ দিগদাৰ হয় যে কি কেনেকেনো এতিয়া কম্পিট কৰিব কিন্তু মোৰ মতে মাষ্টাৰ্ছ লেভেলতে যদি ভাল ৰিচাৰ্চ প্ৰজেক্ট কৰি পাব্লিকেশ্যন কৰিব পাৰে আৰু চাইণ্টিফিক ইণ্ডিপেণ্ডেঞ্চটো যদি দেখাব পাৰে প্ৰুভ কৰিব পাৰে CVৰ জৰিয়তে কিবা যদি প্ৰগ্ৰামিং কৰিছে কোনোবা এটা প্ৰজেক্টত কোড ডেভেলপমেণ্ট কৰিছে সেনেকুৱা ধৰণৰো যদি লিখিব পাৰে যে মই এইটো কৰিছো আৰু প্ৰগ্ৰামিং বহুত দৰকাৰী চাইণ্টিফিক ৰিচাৰ্চত আজিকালি প্ৰগ্ৰামিং নহলে নচলে প্ৰগ্ৰামিঙত যদি ভাল সেই সব দেখাই পেলাই যদি CVখন বনাব পাৰে তেতিয়া বহুত কম্পিটিটিভ হৈ যায় আচলতে সেইটোৱে আচলতে মই দেখিছো সাধাৰণতে PhD কৰা ল'ৰা ছোৱালীৰ ক্ষেত্ৰত বৰ্তমান কিন্তু PhDটো আজিকালি বহুত কম্পিটিটিভ আগৰ নিচিনা নহয় হ'বলা যোৱা 5-6 বছৰৰ ভিতৰত বহুতখিনি বদলি গৈছে আচলতে আনফৰ্চুনেটলি সেইকাৰণে মই কোৱাৰ কাৰণে এইটো নহয় যে কি এপ্লাই কৰিব নালাগে এপ্লাই কৰিব লাগে খালি এইটো কথা ধ্যান ৰাখিব লাগে যে অন্য ল'ৰা ছোৱালীয়ে ইয়াত ল'ৰা ছোৱালী আচলতে কি হয় মাষ্টাৰ্ছ লেভেল বা বেচলাৰ্ছ লেভেলতে বহুত ট্ৰেইনিং পায় সিহঁতি কেনেকে এপ্লিকেশ্যন বনাব লাগে কেনেকে CV লিখিব লাগে কেনেকে সফট স্কিলছ ডেভেলপ কৰিব লাগে সিহঁতি মানে কাৰিকুলামটোতে সেইটো ট্ৰেইনিং পায় যে ট্ৰেইনিং পোৱা ল'ৰা ছোৱালী এগৰাকীয়ে যোনটো লিখিব তোমাৰ ট্ৰেইনিং নোপোৱা ল'ৰা ছোৱালীয়ে লিখাটোৰ লগত কম্পেয়াৰ কৰিব নোৱাৰি সেইকাৰণে মই ভাবো যে আমাৰ মাষ্টাৰ্ছ লেভেলত বেচলাৰ্ছ লেভেলতে সেইবিলাক ট্ৰেইনিঙো দিয়া হওক যাতে কম্পিটিটিভ হ'ব পাৰে আমাৰ ল'ৰা ছোৱালীখিনিও
আজিকালি একচুৱেলি বহুত কেইটা স্কিমো আছে যে ছামাৰ ভেকেশ্যনত গৈ প্ৰজেক্ট ৱৰ্ক একচুৱেলি কৰিব পাৰে ষ্টুডেণ্টছে বহুত কেইটা ফেলোশ্বিপছ নেশ্যনেল একাডেমি অফ চায়েন্সেছ বা ইণ্ডিয়ান একাডেমি অফ চায়েন্সেছে স্পনচাৰ কৰে বা ইভেন ইনস্পায়াৰ স্কলাৰশ্বিপছ বা তেনেকুৱা ধৰণৰ তো সেইখিনি মোৰ মতে ইউটিলাইজ কৰিব লাগে ডিউৰিং গৰম বন্ধৰ বাবে কাৰণ আমাৰ যিখিনি মষ্ট অফ দ্য আণ্ডাৰগ্ৰেজুৱেট কৰ্চেছ পষ্ট গ্ৰেজুৱেট কৰ্চেছ ৰিচাৰ্চ কম্পনেণ্টটো ইমান বেছি ষ্ট্ৰং নহয় এতিয়া USA গ'লে কিছুমান গ্ৰেজুৱেট কৰ্চেছ ইনক্লুডেড হৈ থাকে বাট ইউৰোপৰ বেছিভাগ জেগাত হয়তো এটা বেছি ভালকে ক'ব পাৰিব পাৰোঁ ৰাইট অফ গেটিং অফ দ্য প্লেন ৰিচাৰ্চ কৰিব পাৰিব বুলি তেওঁলোকে এজিউম কৰিব
সেইটো আচলতে হেৰি মেইন কথাটো হয় কি তুমি প্ৰুভ কৰিব লাগিব ন যে কেনেকে যে ৰিচাৰ্চ ইণ্ডিপেণ্ডেঞ্চটো আছে এণ্ড ওৱান ৱে অফ প্ৰুভিং ইট ইজ চাইণ্টিফিক পাব্লিকেশ্যন যদি চাইণ্টিফিক পাব্লিকেশ্যন আছে দেন যদি scientific publication accept হৈছে বা submit কৰিছে সেইটোৱে এটা first step যে research independence টো আছে আৰু এটা কথা যে PhD topic টো ওপৰতো কথা কিছুমান PhD topic বহুত competitive কিছুমান PhD topic ইমান competitive নহয় আৰু লগতে যেতিয়া এপ্লাই কৰা হয় এটা কথা সোধা হয় যে কি এইটো PhD প্ৰগ্ৰামতে কিয় এপ্লাই কৰা হৈছে কিয় এপ্লাই কৰিছা তুমি এইটো PhD প্ৰগ্ৰামতে অন্য কিহৰ কাৰণে তুমি কৰিছা এইটো তেতিয়া হেতু উত্তৰ দিব লাগিব যে তুমি এইটো টপিকত তোমাৰ ইন্টাৰেষ্ট আছে এইটো টপিকৰ বিষয়ে তুমি জানা আৰু এই টপিকটো ওপৰতে তুমি ৰিসাৰ্চ কৰাৰ আগ্ৰহিত কাৰণ যদি তুমি কোনোবা PhD supervisor তোমাক PhD কাৰণে accept কৰিছে প্ৰগ্ৰামত এইটো এটা funded position আৰু এটা এটা projector part the projector 3 বছৰ পাছত projector report লিখিব লাগিব publication কৰিব লাগিব আৰু projector complete কৰিব লাগিব কাৰণ হেবিলাকৰ supervisor কো বহুত দায়িত্ব দিয়া থাকে তোমাৰ national body বিলাকৰ পৰা funding body বিলাকৰ পৰা তে হেকাৰণে supervisor জনে এনেকুৱা এজন লৰা বা ছোৱালী লব বিচাৰে যোনে এই 3 বছৰ ভিতৰত কামখিনি কৰিব পাৰিব লাগিব ইন্ডিপেন্ডেন্ট হ'ব লাগিব আৰু নিজৰ ফালৰ পৰা কামখিনি কৰিব লাগিব এইটো নহয় যে কি সুপাৰভাইজাৰে ক'ব যে তুমি এইটো কৰা দেন কৰিলে কিন্তু তাৰ পৰা নিজে কিমানখিনি কৰিব পাৰিব হেতু ওপৰত আচলতে বহুত বিচাৰে আচলতে তে হেতু তুমি যে ৰিসাৰ্চ ইন্ডিপেন্ডেন্টলি কৰিব পাৰা তোমাৰ এইটো টপিকৰ ওপৰত তোমাৰ নলেজ আছে তুমি আগ্ৰহিত আৰু এইটো টপিকৰ Exactly, এইটো টপিকে নহয় কিন্তু অন্য টপিকত মই অলৰেডি ৰিসাৰ্চ কৰি থৈছো মোৰ তাৰ পাবলিকেশনৰ প্ৰুফ আছে সেই সব দেখাবলে হলে মানে দেখাব পাৰিলে কনভিন্স কৰিবলৈ সুবিধা হয় আৰু লগতে ইন্টাৰভিউৰ ওপৰতো কথা আছে ইন্টাৰভিউ ললে ধৰা তোমাৰ ইন্টাৰভিউত কেনেকে কি ক'ব লাগে হেবিলাকৰো বহুত কোচিং আজিকালি ইয়াত দিয়া হয় হেবিলাক আমাৰ তাত দিয়া হয় নে নহয় মই নাজানো কিন্তু কোচিংটো ললে আচলতে বহুত কথা গম পোৱা যায় লগতে প্ৰেজেন্টেচন কেনেকে কৰিব লাগে হেতুৰ ওপৰতো বহুত ডিপেন্ড কৰে সো হেসব বহুত কথা আছে যিবিলাক সৰু সুৰা কথা আচলতে কিন্তু সব একেলগে আহি পেলাই বহুতখিনি ডিসিশন মেকিংত প্ৰভাৱ পেলায় হেবিলাক কথা আচলতে শিকাব পাৰিলে ভাল শিকিব পাৰিলে ভাল আৰু আজিকালি অনলাইন ৰিসোৰ্সেসও বহুত আছে যিবিলাক তোমাৰ গুগল কৰিলে বিচাৰি পোৱা যায় নিজেও হেবিলাক বিচাৰি সুবিধাবিলাক ল'ব পৰা যায় নোৱাৰা নহয় সেইকাৰণে হেসব কৰি অলপ হেসব কৰিব লাগে কিন্তু মেইন কথা হ'ল যে কি PhD টপিকটো আগ্ৰহিত টপিকটোৰ ওপৰত অলপ এনে কৰিম বুলিয়ে না PhD এটা লাগে বুলি নহয় মই এইটো বিষয়ে জানিব বেছি বিচাৰিছো সেইকাৰণে মই PhD কৰিব লৈছো হেতু মানে কনভে কৰিব মেছেজটো কনভে কৰিব পাৰিব লাগিব
Exactly. Motivation to have our factor. Oh, yeah, I see a question in the chat box. Man in series along with writing about your experiences, what are more things you should mention so as to get selected? I think more or less a question answer very good, sir. And what we can try from our side is that we Europe, Australia, by US, by Canada, for successful applicants, US scholarship, get help from us. তেওঁলোকৰ লগত এটা সেশন ৰাখি আই থিংক এটা আমি সেপাৰেট সেশনত এটো দীঘলীয়াকে ডিসকাস কৰিলে ভাল হ'ব নহয় জানো
হেতু আচলতে বেছি ভাল হ'ব কাৰণ মোৰ যোনটো এক্সপেৰিয়েন্স এটা অলপ পুৰণা এক্সপেৰিয়েন্স অলপ নতুন হৈ থকা নাই মোৰ এক্সপেৰিয়েন্স বিলাক সেইকাৰণে যিবিলাকে লৈছে ৰিসেন্টলি স্কলাৰশ্বিপ পাইছে তেওঁলোকৰ সুধাটো বেছি ভাল হ'ব
তেনেকুৱা দুই এটা সেশন হ'ব আমি ৰাখিব পাৰিম বুলি আশা কৰিছো Anyway, it's about to be 5:30. If there are no more questions, okay. Let's see one more question. How much important programming is in astrophysics? What are the programming languages we should learn? Is Python sufficient?
Okay. Depend কৰে কোনটো field কৰিছে
Yes.
Okay. So, যোনটো field depend কৰিব কাৰণ তোমাৰ যদি observational astrophysicsত যায় তে Python আজিকালি বহুত ইউজ কৰা হৈছে Python টো জৰুৰী কিন্তু লগতে good understanding of statistics তোমাৰ not only general statistics but also Bayesian statistics এটা জানিব লাগিব বুলি নহয় হেতু proficient হলে ভাল আৰু লগতে যদি থিয়ৰিটিকেল এষ্ট্ৰফিজিক্স কৰা হয়, যদি থিয়ৰি চিমুলেশ্যনছ মডেলিং কৰা হয়, দেন ফৰট্ৰানটো জনা অলপ জৰুৰী, আৰু লগতে কেতিয়াবা C++ জনাটো অকণমান জৰুৰী। কিন্তু ফৰট্ৰানটো আজিও এষ্ট্ৰফিজিক্সত বহুত ইউজ হয়, যদি থিয়ৰিটিকেল এষ্ট্ৰফিজিক্সত যাবলৈ বিচাৰে। তো সেই পাইথন জনাটো যথেষ্ট জৰুৰী, থিয়ৰিটিকেল হওক অবজাৰভেশ্যনেল হওক, কিন্তু ষ্টেটিষ্টিকেল নলেজটো লাগিব বহুত।
Maybe high performance computers খিনি যদি তাত কাম কৰিব বিচাৰে হয়তো C ফৰট্ৰান সেই তেনেকুৱা অলপ
হাই পাৰফৰ্মেঞ্চ
জনাটো
কম্পিউটিং
হয়তো দৰকাৰ।
C++, ফৰট্ৰান খুব ইউজ হয়, আৰু লগতে আজিকালি মেচিন লাৰ্ণিঙৰ নলেজটো জৰুৰী, GPU CPU কেনেকে কাম কৰিব পাৰে সেইবিলাকো জৰুৰী, আৰু লগতে ভাৰ্জন কণ্ট্ৰল such as GitHub সেইবিলাকো ইউজ কৰাটো জৰুৰী।
Okay, so yeah, it's 5:30. আমি শেষ কৰিবলৈ আগবাঢ়িব পাৰোঁ বুলি ভাবিছো। So anyway, thank you so much. আপোনাৰ বিজি শ্বেডিউলৰ পৰা ইমান short notice-ত talk দিবলৈ agree হোৱাৰ বাবে। And I'm sure our participants had a good time. আৰু বহুতখিনি নজনা কথা শিকিলে। বহুতখিনি হয়তো questions লৈ ঘৰলৈ গৈছে, যিখিনি questions-ৰ উত্তৰ বিচাৰিব বুলি মই আশাবাদী। So anyway, thank you so much. Any final remarks from your side?
নাই, কি ক'ম, এষ্ট্ৰফিজিক্সত ইণ্টাৰেষ্ট আছে, আগবাঢ়ি যোৱাটোৱে আশা কৰিছো চব সকলোৱে যাতে, আৰু ফিজিক্স, এষ্ট্ৰনমি, প্ৰগ্ৰামিং, ষ্টেটিষ্টিক্স সেইবিলাকত অলপ লাগা আৰু যাৰ ইণ্টাৰেষ্ট আছে, আৰু পাৰ্চিষ্টেঞ্চ ইজ দ্য কি, চ' সেইটোৱে মোৰ লাষ্ট টেক আৱে, আই থিংক, পাৰ্চিষ্টেঞ্চ, লাগি থকা যোনটো লাগিব বিচাৰে।
So yeah, thank you so much. I extend my thanks to the participants also. Okay, so here we can conclude everything. Thank you so much.
Yeah, thank you. Bye-bye.
Bye-bye.